Okay, perfect. Yes.
Okay.
We are good to go. So, yeah, well, thank you so much, Kate, for agreeing to contribute to this school. So just an introduction, very brief. Kate Scholberg is really extremely well known in the neutrino world. She's the spokesperson of the coherent experiment that discovered and detected for the first time the coherent neutrino nucleus interaction. And among that, apart from that, she's also part of the T2K and the Dune experiment, and also is a member of the Super Kamiokande. So really everywhere where a neutrino is. So please, Kate, I don't want to take more of your time. Start whenever you're ready.
Okay, thank you. Thank you for that kind introduction, and thank you for having me. I'm sad not to be there in person, but we can hope in the future it will improve, but I'm glad we can have a good virtual meeting. Okay, so I'm going to tell you that, well, the title of my lectures is Scattering in Neutrino Alley, but it's actually kind of an excuse to talk about a range of things. So I'm actually going to talk about a whole bunch of things which are background for what will eventually be in the last lecture, which will be more about actually Neutrino Alley, which is a location for a neutrino scattering experiment called Coherent at the spallation neutron source. But I'm going to go through a lot of background information before I get there. Let's see. Okay, so here is an outline of what I'm going to talk about. And so today, and I guess we'll see how it goes. I'll see if I can finish the material. If not, I'll rearrange. But today I'm going to talk generally about neutrino sources. I'm going to talk about neutrino interactions, kind of generally, and also particle detection techniques, also generally. And I think you've seen some of this material in some of the other lectures, but I think that's okay. It's okay to see things in multiple ways, in multiple instances. So that's going to be today. And so that's kind of starting with a very general topics. And I'm going to get gradually more specific. And so tomorrow I'm going to talk about neutrinos in the low energy, where in this case, low energy means maybe a few to 100 MeV range, maybe 10 to 100 MeV range. And then specifically physics you can do with neutrinos from pion decay at rest. And then I'm finally going to get, after all of this background information, I'm going to get to a specific example of the spallation neutron source and the pion decay at rest source there, and the coherent experiment, which makes use of it, and some of the future prospects. So I'll start today just generally about neutrino sources. So start there, and you've heard this before in more detail. Neutrinos are, of course, neutral partners of the charged leptons. We have three flavors, three families. They are tiny mass, and they have weak interactions, also gravitational. The sources come over a huge range of energies, down from very, very low energies where you have relic neutrinos left out over after the Big Bang, up to extremely high energies from natural sources. I remember this, my mnemonic for this is my God, that's pretty energetic. That's how I remember the sequence there. And the very highest energies, PeV, EeV, from exotic cosmological sources. I'm actually going to talk mostly in the middle here, from the MeV to tens of MeV range later on. And then there are, so these are natural sources. Supernovae, the sun, the atmosphere in the middle range. And then you can also make neutrinos artificially, and they're so-called tame sources, although it's not always, tame doesn't always mean you understand them perfectly. In contrast to wild sources, sometimes you even understand those better than the tame ones. And here we have neutrinos from nuclear reactors, which I think you'll hear a lot about at this winter school. And neutrinos can be made in accelerators in different ways. You can make artificial radioactive sources. And there's what I'm actually going to spend more time on is neutrinos, a particular kind of accelerator source where you stop pions and they decay at rest. So here's just another visualization of these different sources and the range of energies that they have. This is the so-called grand unified neutrino spectrum at Earth, showing the flux as a function of energy, otherwise known as the spectrum, over all of these orders of magnitude of energy. for neutrinos from these different natural sources. And there's one artificial source on here, which is the reactors. So this is presumably some particular location at the Earth. And you can see there's a kind of a power lawish behavior over much of it, but it's an enormous range. And this is the region here in green over which one can create, or over which humans have created neutrinos from accelerators. So those are the artificial kind, and we're going to eventually zoom in on the low energy part of that. Okay, so the next general thing is neutrino interactions with matter, and I know you've seen some of this in some of the other talks. I think Dr. Gramellini's talk covered this as well. So there are two basic kinds of neutrino interactions, the charged and the neutral current kinds at the fundamental level. And a charged current interaction will create a lepton in the final state. So this occurs by exchange of a W boson. And you've heard this from, I'm sure, Roni and Pedro, where experimentally, as an experimentalist, you think of this as an interaction where you have a lepton in the final state with the same flavor as the neutrino in the initial state. This is, of course, the standard model kind of interaction. And you, of course, in order for this interaction to happen, you have to conserve mass energy. So you have to have enough energy to create that lepton in the final state. So if you have a muon, you need to have, at least in the lab frame, at least about 100 MeV. For a tau particle, you need about 3.5 GeV to actually create that lepton in the final state. Then there you have neutral current interactions, which can create new particles in the final state, or they can be just scatters. And these occur by exchange of a virtual Z boson, and they do not care about the flavor. They're basically flavor blind, modulo minor corrections. It's basically a rate that does not depend on the flavor of the neutrino that is going in. Okay, and so weak interactions, just to give you a scale, compared to, for example, photon interactions, if we're thinking about neutrino interactions with matter. So on the left-hand side, what I have here is a plot from the particle data book showing the cross-section for interaction of gamma rays, or gamma and X-rays with carbon. And so gamma rays are photons that are famously penetrating, so famously relatively weakly interacting with matter. And you can see here, if you have, say, a 1 MeV gamma ray going through carbon, the cross-section, units of centimeter squared, is about a barn, which is a unit of 10 to the minus 24 square centimeters. And so that's a kind of typical energy, or a typical cross-section for interaction of an MeV photon with matter. If you contrast that to neutrinos, this is a plot here of interactions of neutrinos in that same energy range. So say a few tens of MeV with carbon. And here the cross section, you can see here, there's like a 10 to the minus 38. And it's about 16 or 17 orders of magnitude smaller. So there's very weak interactions with matter. And I'm going to get to this a bit later, probably in the lectures tomorrow. In the lecture tomorrow is if neutrinos are a messenger for astrophysics, for example, if you're trying to use neutrinos to learn about, for example, the sun or supernovae, this very weak interaction is actually, it's both a very good thing and a very bad thing. And the very good thing is that the neutrinos, if you can see neutrinos emitted from an astrophysical source, you can see what is happening very deep inside that source, because the neutrinos emerge from a region where the photons are trapped. If you're wondering what this picture is, it's from a Google image search of ghosts escaping. So you can think of the neutrinos as escaping from a very dense region, and you can learn about what is happening in that region from observing the neutrinos that escape. But the curse part is that the neutrinos are so weakly interacting that you need very large detectors or very, other extreme measures, such as going deep underground. You can't just set out a detector of human size. Usually, that's not completely true, but in general, you need it's very difficult to detect neutrinos. And so that's the bad part of the weakness of the weak interaction. Here's some nomenclature. I think you've seen these similar images in the earlier talk today from Elena Gramellini. This is just some nomenclature. An elastic interaction, typically there's actually some slightly different conventions about this nomenclature, but typically if we talk about an elastic interaction, that means that the same particles go in as out. I mean, in some sense, everything is elastic in the sense of conserving energy on a microscale, but applied to a particle interaction, it usually means same particles in as out. A quasi-elastic interaction is when you can have different final state particles, but basically the same number of particles. You're not creating new particles. So an example would be a charge current interaction where you have a lepton in the final state. So it's not the same particles in and out, but it's still a simple interaction. An inelastic interaction is when energy gets converted to new particles in the final state. And so, for example, you can create some sort of particle that's made of quarks that then decays, or you can create hadrons, or you can excite a nucleus, and it can be excite. There's some of the energy that the neutrino had gets converted into some kind of new particle. Okay, and so here are some instances of in the low energy range, and here I'm going to talk about the things that are most relevant in the low energy range. There's you can actually have deep inelastic interactions. You probably heard about that. That's when you have neutrinos that are scattering off quarks and they make a huge mess and stuff flies out all over the place. That's not so much what happens if you have neutrinos of less than 100 MeV. You can have inelastic interactions and debris flying away, but it tends to be less violent. So I'm categorizing interactions that you can have for neutrinos with matter in the few to few tens of MeV range. And you can have charge current interactions and neutral current ones. And the simplest kind of target is scattering of neutrinos on electrons, and that can occur via a charge current channel or neutral current contributions as well to the scattering. For protons, which is maybe the next most complicated target, electrons is very simple, protons are also very simple. You can have a charge current interaction, inverse beta decay on protons, and the nomenclature in this field is that inverse beta decay usually refers to electron antineutrinos on protons. Strictly, it would refer to any kind of charge interaction on a nucleus, but the convention is usually what that means is on free protons. So if you have an electron antineutrino interacting on a free proton, it will make a positron in the final state. That's your lepton, which can then annihilate on atomic electrons and make a pair of gamma rays, of 511 MeV gamma rays. Or you can also have a neutron, which can then also capture and create gamma rays. So that has a slightly more complicated final state. This is a very important interaction in experimental neutrino physics historically. Then you can have a neutral current interaction, which is a neutrino scattering off a proton. And a proton compared to an electron is like a big, it's more maybe like a billiard ball, and it's easier to hit the billiard ball with a neutrino compared to an electron, so the cross-section is higher, but you get very low energy recoils. Then a slightly more complicated target, you can have a neutrino interacting with a nucleus, and with essentially a nucleon inside a nucleus, where you have a charge current interaction and you change the nucleus into another species with a neutron converted to a proton or a proton converted to a neutron. And you get a lepton in the final state. And you can also have, it can also be inelastic in the sense you can have, you can leave the nucleus in some excited state. So some of that energy is used to excite the nucleus. It can then de-excite by spitting out some nucleons or spitting out some gamma rays or something like that. The charge currentness of it is the fact that you've got a lepton. Experimentally, you see a lepton in the final state. You can also have a neutral current inelastic interaction. You can have a neutral current excitation of a nucleus where also you get, for example, neutrons spit out. You can have gamma rays that results from a de-excited nucleus later after the interaction. And then you can have also, and so if this proton elastic scattering is like a ping pong ball hitting a billiard ball, this kind of interaction, coherent elastic neutrino nucleus scattering, is like a ping pong ball hitting a boulder. It's very easy to hit it. It has a large cross section, but you have very low energy recoils. And I'm going to come back to that. I'm going to talk a lot more about that interaction later in the lecture. And so these are more complicated final states. Okay, and so this is the interaction rate. This is a very simple expression, and I have to say I probably use this expression every day in my life, in my experimental life. Maybe not quite every day, but more than once a week. It's just a very simple kind of scaling thing. The rate of interaction, it's the flux, which has units of inverse area times time, times the cross section, which has units of or dimensions, I should probably say, of area, and then times the number of targets. And what you get is interactions per time. And so this is a very straightforward expression to figure out how many interactions you're going to get of a particular type in a particular target for a particular neutrino flux. And this scales with the number of targets, so it scales with detector mass. So the number of interactions you get will just be linear with detector mass. And it scales for a isotropic source, or even a non-isotropic source, generally any kind of source that is spreading out, as 1 over the distance squared of, because the flux is just 1 over area that spreads out as 1 over distance squared. And I should note here that the fluxes and the cross sections are, in general, energy dependent. And so you usually have to do a more complicated computation. I will do that later. And so here, this is the back of the envelope expression I use all the time. Here, this is the number of interactions. And here, that's just multiplying the rate by the time. And so I'm going to pause here, and we'll take maybe a minute. I have a poll here. Let's see if I can figure out how to do the poll. And so here's the question. Is how many solar neutrinos will interact in your body during your lifetime? So I want to get a order of magnitude estimate for this. And if you want to write down these numbers, this is a typical electron scattering cross section. So this is actually scattering of neutrinos on electrons. So here's a representative number for electron scattering cross section at a typical solar neutrino energy of a few MeV. And the flux from the sun on Earth is given by approximately 2 million per square centimeter per second above a few MeV. And I'll talk more about solar neutrinos, I think tomorrow. So let's do that. So here's the poll. Let's see if I can start the poll. So maybe I'll take 1 minute to let you write this down and do the calculation quickly. So let's see if I can figure out how to do the poll. So go here. Now it seems to be lost again in the. Yeah, I'm actually not. Here it is. Okay. So here's the first poll. So I'm going to launch the first poll. Okay. So it seems like it's. Do you see 1 poll or 2 poll?
More polls, yeah.
It's just 1? Okay.
No.
There are
5.
2.
There are 2. Okay. So
No.
Oh, no, 5.
You can continue and see every question. There
Okay.
are 5.
Oh, sorry about that. I will fix that.
Okay. All right. So this is the first one. And so there's 5 possible answers in grand order of magnitude. Of course, the exact answer will depend on your exact body size and composition. But just a possible. So all right. So I will wait a few minutes and then end the poll and see how you do. I don't know what everybody else is seeing. Okay, I think I see some people are answering the other poll. Okay, well. I'm not sure. Have people voted? Means we need to fill the other polls. Oh, you actually have to fill them all. Oh, okay. So something is okay.
Oh, sorry about that.
Oh, there's a whole bunch of them. Okay.
Yeah, okay. I will create the next one so you have them ready when you get there.
Okay, so you have a preview.
Yeah.
You have a preview of all the future polls. Okay,
sorry.
That's okay.
Maybe we can answer in the chat.
Yeah, let's do this
This
one
time?
and answer in the chat. Okay, let me close this one. Okay. Oh, that's okay. How do I get rid of this poll here? Go here. Okay. All right. So I think I see a bunch of C's. I see 10 to the -6. I see some A's. C, A. Okay. So it's a kind of there's a range. Okay. All right. Well, so the best answer, it's actually something like 5 or 6. And I think somebody had that. So if you run through the numbers, it comes out to about 5 or 6. So in your whole lifetime, you will, if you use that back of the envelope expression, you're going to have something like, I don't know, maybe 5, maybe 10, depending on your size. You'll have about that number of solar neutrinos interacting as elastic scatters on electrons in your body. Now, if you count up all the interactions, in fact, some of the other answers might be better. But here, I guess I specified electron scattering. So the ones who answered bigger numbers are not really wrong. If you actually include 7s, and so it might be closer to D or E. But if you include only elastic scattering on electrons, it's C is the best answer to this one. Okay, so let me move on to neutrino detectors and what we want in a neutrino detector. And I don't know, probably most of you are not old enough, but when I was younger, the Star Trek The Next Generation was a popular show, and there's a character on it called Geordi LaForge who had this visor that could see neutrinos. And so this is something I've always wanted. And so what do we want? I mean, what we actually want from, if I had a magic visor that would allow me to see neutrinos, a magic neutrino detector, what I'd want to know about those neutrinos is I would want to know what the flavor of the neutrino is, because usually we're studying things like oscillation, which I think you've heard about. You want to actually tell whether it's an electron or a muon or a tau flavor neutrino. You also typically want to know whether it's a neutrino or an antineutrino. You want to know its energy. You often want to know what direction it came from. Sometimes that can help you reject from background or tell you something else, such as where it's coming from, what the source is it's coming from. You typically want it in real time, and sometimes you want to know precisely the time. You want to know the time of interaction. And you also often want to know the position of interaction in the detector. Usually that will help you reject background. And you always want, these are generic things, you want to have lots of them. So you always want lots of neutrinos, and that usually means you need very big detectors, and you need detectors that have high efficiency for detecting particles, and you want low background. So these are all very, very generic properties, and backgrounds can be very high if you're looking for a very low energy subtle signal. And you don't, of course, actually detect neutrinos directly, because neutrinos just go through things in straight lines unless they interact. You can only see the products of the interaction, of course. And so what you actually see is the secondary final state charged, usually charged or strongly charged particles that come out of the interaction. So for this elastic interaction in this particular example, if you have a neutrino scattering off an electron, what you see is the electron that is smacked, that is kicked by the neutrino and then goes flying off, and it's that electron that you detect, which gives you imperfect information about the neutrino that went in just physically, because so the neutrino, when it leaves the interaction, also takes some energy. So you can't get, you from seeing, even perfectly measuring the scattered electron, you still don't have all the information about the neutrino that kicked the electron. Then the quasi-elastic, same thing. You can sometimes see both particles in the final state, and then you can actually fully reconstruct what the information of what the energy of the neutrino was, for example. And then for inelastic interactions, these can be messy. These can have lots of stuff flying around. Some of that energy could be lost. Some of it could be neutrinos if it's a neutral current inelastic interaction. And that would, for example, then you also you intrinsically cannot perfectly reconstruct what the properties of the incoming neutrino was. So there's no such thing as Geordi-Laforge's perfect visor. You always have to somehow figure out the best you can what the properties of the neutrino were given the observable debris from the interaction. And sometimes it's even tertiary particles, showers, other more complicated things. And so this is the experimentalist job, and it's a difficult job, is to try to figure out as much as possible about the neutrino given the stuff that is in the detector. And even that stuff is hard to detect perfectly. In a real life detector, there are always detector resolution limitations. Okay, so here is the next, this probably should have come earlier, but here's the next one. I think you already filled out this poll. I don't know, should I try it again? Is it ready? I think I can try.
Yes, it should be ready.
Okay, let's try. Seem to always lose the full control. Is it here? It's here. Yes. Okay, great. Okay. All right. This one should be an easy question. So inverse beta decay, here I'm talking about what we usually call inverse beta decay, or IBD, which is electron neutrino on a free proton. So this is just a nomenclature question, naming question. What are the, let me launch the poll. How would you name this interaction? So go ahead and try this one. I think this is an easy question. Okay, so I think we've got, I guess I should wait until we have some, I guess it's like listening to popcorn in the microwave. I have to wait until I don't see too many added. Okay, so I will end and we can look here. Okay, so that is the right answer. I think this is the best answer for this is it's charge current. It creates a lepton in the final state. It's an exchange of a W boson, and quasi-elastic is the best name for it because it has different particles going in and coming out. And it's simple final state. It's not, you're not creating extra new particles. I mean, it's a somewhat fuzzy distinction sometimes, but this is probably the best answer.
Kate, we haven't seen the result of the poll.
Oh,
I think you have to
okay, there we go. Okay, I clicked on it. How's that? Can you see it?
Yes, perfect.
Okay, great. Okay, so everybody did well on this one. Okay, so let me stop that. Seems like this, I can't move the poll window, but I can move the other bar. Okay, here we go. All right. All right, so next, okay, here's another question. This is another question for you. And actually, I think this one is not a poll question. Oops, that was the answer. So you didn't see that. This is a question where people can answer either by voice or in the chat. So here's a question. So supernova neutrinos, and I'm going to talk about those more tomorrow, they arrive in a burst containing neutrinos and antineutrinos of all flavors. So electron, muon, and tau, and they're antineutrinos, and they have energies up to about 50 MeV. And here's a question. So why are only electron flavor neutrinos visible via the charged current interaction? Why are there no muon neutrino charged current events? Why are there no muons in your signal? Even though there's muon neutrinos and tau neutrinos, why are there no muon neutrinos and tau neutrinos in your signal? Anybody want this? So it's not a poll. Anybody want to type an answer or say an answer? No takers? Yes. Yes. It's basically, there's not, yes, exactly. So there's not enough energy. If you want to create an electron in the final state, you actually have to create the mass energy of that electron in the final state. And you actually need about an MeV, MeV-ish to do that. That is, that's possible if you have a 50 MeV neutrino. So that 50 MeV electron neutrinos are above charge current threshold, and it is possible to see charge current electron flavor neutrinos, but you actually need about 110 MeV or so if you're a muon neutrino and you want to make a muon in the final state. Muons are about 200 times heavier than electrons, and so if you actually want to create a muon from a 50 MeV neutrino, you can't do it because there's not enough energy. 50 MeV neutrinos are below charge current threshold for muon neutrino production or muon production. And so, so yes, that's right, there's not enough energy, and it's even worse for tau neutrinos. You need about 3.5 GeV to create a tau neutrino in the lab. If you have a tau, or to create a tau lepton in the lab if you have a tau neutrino. And so that means that if you're a 50 MeV neutrino, you can only see it via either via a neutral current interaction. And so here's a plot, and I'm going to come back to the spectrum. This is the kind of spectrum you expect for supernova neutrinos. So the colored lines are the different flavors from a supernova neutrino spectrum. So you have electron antineutrinos, and the green is all the other flavors combined. And you can see they go up to less than 100 MeV, so maybe 50 MeV or so. And these vertical lines are the thresholds for the interaction. And so for inverse beta decay, you have a threshold of about 1.8 MeV. So you can see all of the spectrum to the right-hand side of that line. And for other interactions that are charge current, the thresholds are somewhere from a few to a few tens of MeV. And so you can see some of that spectrum. But here is the threshold for seeing a muon charge current interaction, and it's all below that threshold, so you'll never see it. You need to have a neutral current interaction if you want to see those. And that will become important later when I talk about some other things in the next couple of lectures. Okay, and I mentioned before, so a few slides ago, when we had our back of the envelope calculation, this is the simple form. In practice, you have, that would be for the average values. To do a detailed calculation, in practice, the flux has an energy dependence. It's a spectrum of energies. So like this one for supernova neutrinos, you have a bunch of different energies. The cross-section is also energy dependent. And also detector response is energy dependent as well. And so if you actually have a spectrum of neutrinos, you have to fold the flux and the cross-section and the detector response to actually get to compute the kind of response you will have in your detector. So you have to basically consider different contributions from different energy bands. And so this is the kind of calculation that one does in practice, after understanding a detector response. Okay, so let me now talk generally, and actually this is some of this is a bit of a detour, but this is all good basic information that it will be useful for understanding neutrino detection. I'm going to tell you about particle detection in general and energy loss in general. And so put this material in your pocket, and some of it you'll take out later. And so I'm going to talk actually not so much about neutrinos now. I'm just going to talk generally about the detection of particles, of charged or strongly interacting particles in detectors, since that is actually what you're doing. A neutrino detector is actually detecting the products of the neutrino interaction. So the detection techniques are similar to detection techniques for any charged or strongly interacting particle. So I'm going to talk about detection of charged particles, photons, and neutrons. I should say charged or electromagnetically interacting particles. I just want to point out this reference. If you're an experimentalist, this is an essential reference. This has very important information. This is a great book that tells you really all the basics that you need to know about particle detectors. This is also a good review. There's a particle data group. If you go to the back pages of the particle data group review of particle properties, there are concise articles that summarize a lot of very important information relevant for particle detection. So I would give you this as a very good reference if you're experimentalist and interested in particle detection. Okay, so particles lose energy, and it's that energy, the energy they transfer to matter is how you can actually detect the particles. You can actually, that energy gets converted into something that you can then turn into a signal. And so I'm going to first talk here generally about particle energy loss in matter. And they deposit momentum as well, in the sense that they can deposit energy, but they can also change direction as well. And common energy loss processes are inelastic collisions with atomic electrons. So you have a charged particle going through matter, it's smashing through the electrons in an atom, and it can be kicking those electrons, ionizing them, exciting them, basically, just transferring energy into the atomic system. So you can have excitations and ionization. So the excitation is just when you have a electron and you excite it to another level. And ionization is when you're exciting it to infinity and the electron gets separated from its parent atom. And you can have other secondaries associated with that too. You can have elastic scattering from nuclei as well. You can also have Cherenkov radiation, and I'll say more about that. There's also some more, these are the common energy loss processes. If you shoot a charged particle into matter, this is mostly how the energy loss will occur. But there's also some rare processes which might not happen a lot, but they still happen often enough that they can be an important part of a detection distribution. So these are interactions with nuclei, nuclear reactions, and also bremsstrahlung, which is what you have from charged particles losing energy. Okay, and so for normal cases here, and so here, oops, I'm first going to talk here about something has gone funny here, about so-called heavy particles, meaning heavier than electrons or positrons. So this would be muons, which are 200 times heavier, pions, kaons, which are yet heavier, mesons, and also protons and alpha particles, and even nuclei. And so in normal cases, most energy loss comes from these inelastic collisions and mostly ionization. And this is a jargon, a stopping power, or DEDX is the energy loss as a function of distance traversed in the material. And it depends on the projectile, it depends on the material, it depends on the energy of the projectile. It's actually, the basic approximation is calculated in Jackson. It's classical electricity and magnetism. I think you've heard some about this from one of the previous talks today. And it's a statistical phenomenon, but when you have a lot of collisions, it's enough statistics that you don't have very large fluctuations. So you can approximate it well by a mean value in many cases, not every case. And this is the expression, this is the famous expression for energy loss of relativistic particles. This is a quantum mechanical calculation, the so-called beta block equation, which gives you the mean rate of energy loss as a function of these many things, as a function of the projectile and the material. And this expression, actually the analytic expression is pretty good. It's good to maybe percent level for MEV, GeV scale kind of particles, and sort of intermediate materials, not the very light or the very heavy materials. So just to zoom in on some of the quantities in here, This row here, this is the material density, and it's proportional. So the energy loss is proportional to the material density. The expression, if you look in the particle data book for the stopping power, is actually by default divided by density. So it's MeV centimeters squared per gram. And so I'm actually going to sometimes drop this row, but in practice, you often need to multiply by it. So that's a gotcha if you're doing these calculations, just to remember what the convention is. Zooming in on some of these other dependencies, if you actually look in this expression, most of these quantities, actually a remarkable expression, is most of the quantities are really basic physics constants. You know, they pop up in lots of other places, which is actually, it's actually kind of an amazing expression. There are a couple of exceptions, and one is the delta, which is an empirical measured so-called density correction, and the mean excitation energy for the atom type, and that's also a measured quantity. And so this is what the function looks like if you plot the function, the beta block function. Whoops. It's usually drawn on a log-log scale. And it looks like this. It's got, as a function of beta gamma, which is momentum over MC here, it's it's got this shape where you have at very low energy, you have a very rapid increase of energy loss. At high energy, it increases, but increases slowly. And so that's called the relativistic rise as the particle gets more and more relativistic. And it's got a dip here, which is a minimum. And a particle that is sitting here with this value of beta gamma is called minimum ionizing, or MIP, MIP. Minimum ionizing particle is a MIP. Another dependence here is this coefficient here. Z is the number of protons, A is the atomic number of a material. And the energy loss is proportional to Z over A. And that's actually doesn't vary that much by materials. Most materials have about twice as many nucleons as protons. It's sort of roughly divided between neutrons and protons, usually somewhat more neutrons, but it's approximately 0.5. And so this doesn't depend a lot on the target material. And so here's just the example here. This is as a function of the beta gamma here for different materials. It also depends on, this is the beta here, and here's the beta gamma that shows up here. These are the relative, this is, by the way, this is the relativistic gamma. And you can see here, you basically have the same shape of the curve, and you can slide it back and forth for different particles, for a muon or a proton or a pion. It looks the same in shape, but you can read off different scales. Here's a terminology note. I think I said this, a MIP, minimum ionizing particle. And the reason that this is so common to talk about MIP, I always used to think when I first heard about this is, isn't it weird to be talking about the particle right at the minimum of this curve? But in fact, the relativistic rise is so slow that it's actually often a perfectly good approximation to assume that any particle that's zipping through a material is not too far from minimum ionizing. And that value is, and if you know this rule of thumb, you can estimate this energy loss for pretty much any material just by the scaling of the beta block equation. It's about 2 MeV per centimeter for a muon in water. That's a good rule of thumb. Okay, and so this is an aside. This is not this is just a fun side note. This is something I think is cool, is that you see this very rapid rise at low energy. So if you have a particle and it's slowing down, the slower it gets, the more you're as you're losing energy, you're slowing down and you're moving along this line to the left. And so once you pass the minimum ionizing, you are losing energy faster and faster. So you increase your energy loss more and more as you slow down. And so you end up with not too much energy deposition. And then right before you stop, you deposit a lot of energy. And this pattern here, this is energy deposition as a function of depth that a particle penetrates into tissue. This is actually biological tissue. You actually get lots of energy right at the end of the track. And this is actually, this is important in particle physics too, but I think it's a kind of cool application that this is actually used for cancer therapy, in that if you have a tumor and you want to kill it with energy loss of particles, if you can arrange for that tumor, shoot the radiation at the tumor such that the particles deposit all their energy right at the end of the track, that can actually be helpful for killing cancer. And so that's a kind of a nice application. It actually is also useful for actually learning about particle energy in for non-biomedical applications. But I thought I would just mention this if you didn't know it. Okay, this is just a warning, just to say, so this is the stopping power here. Just to warn you that if you go beyond the sort of medium energy, things can go a little wonky. They can go a little crazy. So this beta blockish area here is kind of normal particle energy loss. But if you go to high energy, so here we're talking TeV, this is muon momentum here, this is TeV per C muon momenta, you actually start to get different shape. I'm actually going to talk about the Bremsstrahlung energy loss in a bit. And it can be much higher energy loss rate. If you go to low energy, that's also funny. It doesn't follow this beta block kind of energy loss. And that is actually can be very important for experiments where you're trying to understand very tiny energy depositions. That's a, a whole can of worms. It's a whole area of detector science trying to understand how energy loss happens at very low energy. And it's not standard beta block. Okay, so let me move on. I'm going to start talking about light particles. We were talking about heavier ones, heavier than electron, but electrons actually act differently. So they are light. They don't just ionize stuff. They also they're light, so they ping off things and they bounce around. They can be deflected. Accelerating charges radiate photons. This is what's known as Bremsstrahlung. And the probability for Bremsstrahlung, for radiating a photon, is inversely proportional to the square of the mass of the particle. And so for electrons, you are much more likely to get Bremsstrahlungs than Bremsstrahlung gamma rays, or photons, it can be, I guess, X-ray, than for a muon. A muon is heavy, so you get many, many fewer Bremsstrahlungs. You have to have much higher energy to actually Brem. And this you can hear, actually you can see that on here. This is Bremsstrahlung for a muon, and it doesn't really turn on until quite high energies. That's not true for photons. Photons at 10 MeV or so will Brem. This is some terminology. At a few tenths of MeV, the Brem energy loss is, and depending on the medium, the Brem energy loss will be greater than the ionization energy loss. And where that crosses over is called the critical energy. And this is the approximate a formula, sort of semi-empirical formula, I think. And a typical critical energy, so the critical energy is where in a material you will start to get substantial Bremsstrahlung, or Bremming for short. And you can see for these materials here, it's something in the range from a few to 100 MeV. Maybe I'll skip this, but I'll just talk here about energy loss of photons now. And when I talk about photons, there's optical photons. That's not what I'm talking about right here. I'm talking about photons of high energy variety, so X-rays and gamma rays. Photons don't have electric charge, so you don't have Coulomb-induced collisions like electrons. There are 4 different energy loss mechanisms, which are important for particle detection and neutrino detection. That's photoelectric effect. Well, 3 that are most important: photoelectric effect, Compton scattering, and pair production. And most of these actually destroy the photon. If photoelectric effect, you'll get absorption of a photon, and then that photon is gone. It's dead. There's no more photon. There's an electron scooting off somewhere, but there's no photon. Same for pair production. Pair production is when you create an electron-positron pair, and that is also no more photon. It's a pair. And so just zooming in a little bit on all of these, the photoelectric effect here is you pop an electron out of an atom, And that dominates at low energy, so less than 1 MeV. So this here is, actually, this is an example cross-section. I think I showed you a version of it earlier. This is the energy of the photon. So here we're talking, this is X-ray energy, this is gamma ray energy around here. What you have at low, and so this is on carbon. And so at low energy for X-rays, the photoelectric effect dominates. That's what that greenish line is. And so you're most likely that the photon will be sucked up by an electron in an atom, and then that electron will zip off. It will ionize that atom. Then at slightly higher energy, so here in this region here, 1 MeV or so, you actually have Compton scattering. And actually this is a phenomenon, this is very important in neutrino physics in the GeV range that I'm going to be talking about, is the photon comes in, it smacks an atomic electron. The photon isn't destroyed, it gets scattered, but the electron gets scattered away. And this is kind of dominant in this region. It's basically what will happen is the photon will smack electrons, and the electrons you'll get a bunch of smacked electrons, and it's those electrons that you see. That's what's actually visible in a detector. You actually see little bits of energy deposition that come from the photons that have scattered the electrons. This is just the distribution of energies. This is a so-called Compton edge. Maximum energy you get in such a scattering, and it will tend to be smooshed out because of the detector resolution. Then the pair production is the third one, and this is also important for neutrino physics, is at higher photon energies, so above an MeV or above several MeV or so, that's this pinkish here, you get more chance for there to be an actual creation of an electron-positron pair. So that photon disappears, it turns into an electron-positron pair, and it's that electron-positron pair that you see in the detector. And that also has a kinematic threshold. It requires at least twice the mass of the electron energy. And then these can happen all at once, and this is what's called an electromagnetic shower. And actually this is much more important at higher energies. What happens is if you, let's say you have, you start with either an electron or a photon, you can start that, the electron, let's say you start with an electron, that electron can spit off a photon. Then the photon, if it's got high enough energy, it will pair produce, and then the electron and positron can then brem. So you get this kind of chain cascade of electrons and photons and positrons until all the energy is, the energy decreases at each step until the shower it's a shower, the shower dies out, and then it goes back to photoelectric effect and Compton scattering. And so this is a common kind of avalanche phenomenon that you can image. And if the electron was created by a neutrino, this is how you can actually see a high energy neutrino. But actually, this is really more relevant at high energies. And so here's a question. What do you think, just based on some of the numbers I showed you before, do 10 MeV electrons in argon, do they create electromagnetic showers? Do they create sort of nice patterns in a detector like this shower on the bottom left in purple? So what do you think? I'm going to do the poll. Okay, let's see, electrons in argon. Okay, launch poll, let's see that. Okay, so what do you think? Never, occasionally, or all the time? Okay, so the votes seem to have ended. Okay, so that's the end. That's the distribution. Oh, wait, let's see. Oh, maybe you can see that now. Okay, so the actual answer is probably closer to never. I mean, it's not the critical energy for argon, for electrons in argon, it's something more like 30 MeV, 30 something MeV. And so 10 MeV, you will sometimes make bremsstrahlungs, but the gammas that you get are almost never going to pair produce. And so They might sometimes, so you might get a very pitiful little shower, but the answer is, so occasionally is not maybe exactly wrong, but so it's not a bad answer, but in fact, the answer is closer to never at 10 MeV. But if you go up to like 100 MeV, then you are going to get showers. So showers are kind of a not so much a low energy phenomenon, but you do have BRAMs and pair production occasionally. Okay. All right. Oh, and actually that's just a picture. That's a picture of and I think you saw stuff about argon TPCs. That's actually a picture of an electron, a 10 MeV electron. It's really just a track. There's not this one particular, you could have a BRAM, but this one is mostly just a track. Okay, let me say something about neutrons. Neutrons do interact by the strong force. That's a short-range force, and so interactions tend to be rare. The neutrons will tend to penetrate materials. In fact, if they're your background, they are terrible. They drive you crazy. They tend to float around and get into cracks and make they're bad. Well, okay, the experiment I do hates neutrons, but maybe you like neutrons if you're trying to measure them, but they tend to be sneaky and ping around all over the place. The main mechanism of energy loss is elastic scattering from nuclei. And so the neutron will, by strong interaction mostly, will smack into a nucleus, and it will send that nucleus recoiling. And so what you would then see is the energy loss of that recoiling nucleus. You can have other inelastic interactions. You can excite nuclei and see the excitations. You can capture. So nuclei like to sometimes eat neutrons. If they don't have a lot of neutrons, they like to swallow them. And then they often have an excited state. And then that you get gammas that de-excite. That you need to have slow neutrons for that. There can be other interactions. You can also, at high energy, the neutrons can smash into things and make big hadronic showers at very high energy. So this is, there are various modes, but at low energy, mostly it's elastic scattering that is the main mechanism for energy loss of neutrons. There are some specialized codes. And I should just mention here, neutron moderation, just to give you some terminology here, is and capture. This is actually a common thing for low energy neutrino experiments, is that the neutron is sometimes a way of detecting a neutron from a neutrino interaction. So this example here, inverse beta decay, you get a neutron in the final state, and that neutron can, for example, capture on a proton or sometimes something else, and it creates a 2.2 MeV gamma. And then what you see is the Compton scatters of that gamma, or also the positron annihilates and then makes two gammas, and then you can see the Compton scatters of those gammas, or possibly photoelectric effect in principle. And so if you want to have a capture, then the neutron has to be going slowly. And so you typically have to wait for it to bounce around and lose energy in a material, or sometimes you can specially devise your detector to do that efficiently by, for example, putting light nucleus shielding around, so water or paraffin or something, hydrocarbons, that's a so-called moderator that will slow down the neutrons on purpose so that they can be captured. Now, there's other reasons you might want to moderate neutrons. Okay, so let me summarize this general particle energy loss topic. So charged particles, the standard normal energy loss is the beta block ionization. For positrons and electrons, it's collisions and radiation, where you have a critical energy where that's the crossover between those energy loss mechanisms. For photons, you have photoelectric at low energy, Compton at medium energy, and pair production at high energy, and very high energy, you have showers. For neutrons, it's really elastic scattering. So these are really the important ones for neutrino detection, or detection of the products of neutrino interactions at low energy. Okay, so now let me talk about detection. Still fairly generic, but I'm going to talk now about neutrino detection also. So generally, detecting is when you want to couple that energy loss into some kind of electrical signal, which you digitize. And from that signal, you have to infer the neutrino properties. You have to infer the neutrino energy, direction, flavor, position, and so on. So that's the whole process. And that's the challenge of experimental neutrino physics, is to turn that interaction into numbers, and then take those numbers and turn them into physical properties. So that's the story. So there are many ways of doing it, and each kind of interaction and experiment will have a different approach. But these are some kind of classic neutrino detection ways of gathering deposited energy for neutrinos detection. So one very classic way is to use scintillation light. So many materials, when they are ionized or otherwise excited by charged particles, will emit light. So you basically excite atomic electrons, which then de-excite to create photons. And then you have photosensors that will pick up those photons and turn them into electrical signals. Another way is, and there's actually many materials, many different kinds of materials, and they have many different ways of scintillating, and I'll say a little bit more in detail about that. Then there's Cherenkov radiation, which tends to be faint light, but still observable. This is a special kind of light emission that you get when the particle is going faster than the speed of light in a medium, so faster than c/n. And so you also need photosensors for that. You can also directly gather that ionization. So when you ionize an atom, you've got a positive nucleus and a negative electron. And so if you have an electric field, you can drift that charge and then somehow detect it. And it's usually the electrons that you will detect. You can gather that charge or otherwise see its signal in different ways. Somehow you have to couple that signal to something you can digitize. And then you can also use heat or phonons. These are special techniques for low energy signals. For example, you can, if you heat up a material, you can look at the change in temperature. If the energy is mostly converted to heat, there's also ways of looking at phonons. And actually these days, there are many new creative techniques for gathering very tiny energy losses, which I'm not going to have a chance to get into, but you may hear more about them in some of the other lectures. And so the specific techniques vary a lot. And actually, you can have often more than one technique in a given detector. So they're often multi-purpose detectors. So I'll zoom in a little bit more on some of these. So just a bit more on the scintillation. So the idea is the particle energy loss will excite energy levels in atomic electrons, and then they de-excite and they can make optical photons. So here photon means like an optical wavelength or UV. And typically the number of photons is approximately proportional to energy loss, maybe not exactly, but approximately over some regime. Often a lot of your life is trying to understand the non-linearities of that. It's because it's not usually perfectly proportional. The emission is usually isotropic for many detectors, so doesn't, it's a glow from a particular energy loss site. It's not directional. You can have inorganic scintillators. These are crystals. Many of these are used, have been used for many, many years, where you have semiconductor kind of detectors that will give you scintillation light. These are quite well understood. Those are often relatively small detectors. Larger detectors, if you want to scale up to a large detector, which is often what you need to do for neutrinos, is you can use an organic scintillator. These are hydrocarbons, typically liquid or solid. Often it's liquid that can be scaled up to a large volume. These are different kinds of hydrocarbons that will actually, you can get a lot of scintillation light from an energy deposition. And then there's noble elements, and these are, for example, liquid argon, liquid xenon, liquid neon. These also scintillate often at low frequency, so at low wavelength, I should say. For example, 128 nanometers for argon, and these are, this can also be used to detect neutrinos or detect the charged particles from neutrinos. The light sensors is an important part of the detector configuration. You have to gather that light and turn it into a signal. And the classic kind of light sensor for many neutrino detectors is a photomultiplier tube. Here, the idea is you make use of the photoelectric effect. You have what's called a photocathode. It's a evacuated tube where there's a material that has a high probability that a charged or a photon will kick out an electron from the surface that then there's a high voltage on here, and the electron will then hit what's called the dynode. And what happens is you get a chain cascade where, let's say you get a photon that comes here, it kicks out an electron by photoelectric effect, and that electron gets accelerated, it smashes into a dynode. You might get 2 electrons come out, and then you keep doing that until you get an exponential shower, and that becomes a macroscopic pulse that you can see. And so this is a very common kind of detector that can be sensitive to single photons with pretty good efficiency. There's other techniques. I'm barely scratching the surface here. In fact, there are many modern, there's silicon PMs are very popular. There's other techniques for photon detection as well. And so many neutrino experiments, because they have to be large, they have to be made of very relatively inexpensive material. And so often it's something liquid hydrocarbons, something like that, in a homogeneous volume viewed by PMTs. It can also be in smaller segments, and noble liquids as well, also in large volumes. Okay, Cherenkov radiation. This is another one I mentioned. And here, the idea is that you get kind of a shock wave of light if a charged particle goes through a medium with an index of refraction n. If the speed is greater than c over n, or beta greater than 1 over n, then you get a kind of shock wave of light. You get this. This is also calculated in Jackson. It's standard electromagnetism. And it has a characteristic angle for a particle that is going close to the speed of light. And that in water is a great material for neutrinos because it's cheap. You can make large volumes of it. And you get Cherenkov radiation. And the number of Cherenkov photons you get is proportional to the energy loss, to a reasonable approximation. So you get, it's actually not that much light yield, but there's a couple of nice properties, and one, or a very nice property, is that it's a directional signal, that if you have an electron going in a particular direction, or any charged particle in a particular direction that is exceeding the Cherenkov threshold, greater than the speed of light in the material, then you get a ring that is in the direction of the particle motion. So you can actually see the direction of the particle, so you get that information. The disadvantage is that there's a threshold. So if you're a heavy particle, for example, if you're a proton, then you have to have more than a GeV before you're above Cherenkov threshold, just from, you just aren't going faster than C over N until you have about 1.3 GeV. And so that means that heavy particles in Cherenkov detectors are invisible. And so that's a drawback. Just to mention here that often it's photomultiplier tubes that see single photons, and that's how you turn the photons. So the particles are deposit energy that is photons that turn into photoelectrons that are amplified and digitized, and then from that information you can reconstruct the energy of the neutrino, the direction it was going in, and where also it happened in a detector. Okay, so ionization detectors, and so this is very generic also here. So the very basic concept is that if you have energy loss, you have ionization, you have nuclei that are separated from their beloved electrons, and you have an electric field to further separate them, and the electrons here, so here's an example, an incident particle is ionizing material. I think you heard about this earlier today in the particular example of a liquid argon TPC. And so if you have an anode, that will attract the electrons, a cathode will attract the remaining positive ions. It's usually the information in the electrons that you lose. Electrons are more mobile. And then you gather those electrons. There are different ways of doing that, of learning about the ionization charge, which is proportional to the energy loss. by, for example, measuring them on a plate and just measuring the current is the maybe simplest way, but there's other ways of reading that out as well, including on wires like a TPC. This is an example. This is also a classic detector invented many decades ago, a cylindrical wire chamber where you just gather that ionization on a central wire in a cylinder, and you get a pulse out of the detector. So that's a very simple thing. And there's this region here. This is as a function of the voltage that you apply. So if you apply kind of an intermediate voltage, you'll get what's called a proportional counter, where the size of the pulse you observe coming out of the wire has a size that's proportional to the charge of the particle. And then you can have what's called a Geiger region, where you get just a big cascade. You have a cascade of energy of collisions nearby the wire, and so you just get a count. You know, you've heard those Geiger counter, click, click, click. It's not telling you the individual energy of the deposition. It's just telling you, oh, there was a big signal. And that's called a Geiger region. And then there's the lovely TPC concept, which you heard more about, I think, earlier today, where the idea is that you read out the charge and you get a two-dimensional projection on the readout plane, which in this example is a wire readout, either by collecting the charge or also what's called induction, where you read a charge just because the charge is sweeping by the wire. And then you get the third dimension of a three-dimensional track by the amount of time that it takes to get that signal on the plane. And that's the third dimension. And that's why it's called a time projection chamber, is you get the third dimension from the time because the drift time is uniform. And then there's very low energy detection strategies. And this I'm going to get into more in detail about how, if you have very, very low energy signals, you want to try to grab that energy and turn it into something that you can measure. And in fact, there are many strategies here that are actually in common for neutrino detectors and WIMP detectors. So detectors that are looking for WIMP dark matter, which is possibly very heavy particles that interact weakly, that the way you see them is they bump into nuclei, and you want to get that little recoil energy and somehow observe it. And there's a bunch of different strategies for doing this. And one is to use heat or phonons. You can also gather the ionization, or you can also use scintillation. So some of these classic techniques also, if you have very sensitive versions of the detectors, you can see very small energy depositions. And many detectors will also use many of them. Okay, so I think the last comments I'm going to make here about neutrino detectors, I'm going to talk about background. So in fact, in neutrino detector world, a lot of the issues that you spend your time thinking about, if you're an experimentalist, is not even the signal. You spend time thinking about the background. And when I was first a graduate student, my first project that I was given by my advisor was to look at some backgrounds. And I was thinking, backgrounds, that's really boring. But now I realize that it's all about the backgrounds. That's really what you spend all your time trying to understand and reduce. And it's really a lot of experimental life is understanding backgrounds. And so the backgrounds come from lots of sources, but typically for low energy neutrinos, you have to worry about radioactivity in the environment. So all kinds of radioactivity, from alphas, from betas, from gammas, from fission, all kinds of stuff that's in your detector, or it can be in the environment. It really depends on exactly what you're trying to do, which ones are important, what your materials are. And then there's also cosmic rays, which are on the surface of the Earth. Lots of them. You get showers on the surface of the Earth, and there's also penetrating component, which is muons that will actually get all the way underground. You can also have activation. If cosmic rays come in, they can actually create radioactivity, so-called cosmogenics, that is long-lived, that remains after the muon has gone through or the cosmic rays have gone through, so-called spallation products. So these are really, these are annoying. They are a big part of trying to accomplish an experiment. Although I have to say that sometimes backgrounds can be useful because you can actually sometimes, if you know what they are, you can actually use them for calibration. So if you have a background of a known energy, you can actually use that in your data to tell you what your energy level is. So sometimes they can help you. I can make the point here that if you're looking at natural neutrinos, with the exception maybe of a supernova burst, oops, it's sometimes, you can't tell by when an event arrives, whether it's a background event or a signal event. But if you have artificial neutrinos, you can sometimes tell the difference. So if you have a beam, for example, the beam is sometimes pulsed. So it's, bam, 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 and you know exactly when the neutrinos are coming. So you know when they're arriving. And if you have a sharp beam, and this is the case for high energy beams, it's also going to be the case for the experiment I'll tell you about, then you actually can know when the neutrinos arrive, and you can reject background outside of the pulse, and you can also use the events that arrive outside of the pulse to tell you exactly what your background rate is. And so it's very nice if you have an artificial source with a known timing. And just a little bit of nomenclature. 2D factor is the pulse rate times pulse width. It's kind of the fraction of the time the beam is on, and you want a short fraction, which gives you a good rejection from cosmic rays. And then, of course, the other classical thing to do is you go underground to shield yourself from cosmic rays, or you often build shielding around your detector, but sometimes that's not enough. And so you have to actually go deep underground. And that overburden allows you to sometimes do an experiment, even if you don't have a beam trigger, and also look for rare events and so on. And this is just a plot here, and also some terminology. Meters water equivalent is the amount of depth. If you have a particular depth, that would give you the same shielding as that same number of meters of water, because water has a standard well-known density. So you have to scale by the density of the matter. And this is shows you how the cosmic rays attenuate as a function of depth. And so this is kilometers. So if you're 10 kilometers underground, you have many, many orders of magnitude less cosmic ray background than at the surface. And this shows you some of the well-known underground laboratories and how they compare for depth and muon intensity. Okay, so here, this is just a knowledge question, a poll here. So if you hold out your hand on the surface of the Earth, where you're sitting, probably where you're sitting right now, how many muons per second are going through your hand? So let me start that poll. So what's the best answer? Is it 10 to the 5? Is it about 1? This is order of magnitude, or is it 10 to the minus 5? Okay. Okay. All right. And the poll. Show the results. Okay. So the best answer here is actually about 1. It's actually about 1 muon per. It's actually more than 1, but it's definitely closer to 1 than 10 to the 5. So it's probably something between 1 and a few going through the palm of your hand. So that's if you're a hand, that's not so many, but if you're a big detector for neutrinos, that is actually could be a lot. And so let me do the other poll here. So the next one. So now consider something much bigger than the palm of a hand, but which is underground. And so now here, this is another order of magnitude question, just to guess here. So how many muons per second are going through Super K? Now, Super K is a detector that is 40 meters high and 17-meter radius. Underground, it's at 2,300 meters water equivalent. It's about 1 kilometer of rock underground in Japan. And the question is, how many muons per second, so this is a chat here, are going through, oops, lost here, are going through Super K. So let's do that one. approximately. Okay, let me launch the poll. And so this is much bigger than a hand, but it's also deep. Okay. Okay, so interesting spread there. So the answer actually turns out to be about 3. So 1 is actually the closest answer there. So it's about 3 hertz of muons per second, 3 hertz of muons going through super K. And that's, of course, if you think how many hand areas cover super K, that's really an enormous reduction compared to the number of muons going through your hand at the surface. It would actually be nice. 10 to the minus 5 is what you would get at a much deeper mine. So that's would be nice to be deeper, but still it's pretty good reduction. It's super K. Okay, so I think I am coming to the end. Okay, so here's the takeaway points from this lecture, just to summarize. So neutrino sources, lots of sources of natural and artificial nature over many orders of magnitude and energy. We're actually going to zoom in starting next lecture into the medium, kind of 10 to 100 MeV range. Neutrino interactions, terminology you should know: charge and neutral current, elastic, quasi-elastic, inelastic. This is my favorite expression for calculating event rates, just back of the envelope. So this is a good one to know. Neutrino detection, neutrinos, you see they're secondaries or tertiaries or more. Particle energy loss for charged particles. Ordinary is beta block. It can be a little different outside of that range for electrons and positrons, collisions and radiation. Photons, 3 energy loss mechanisms. Neutrons, mostly elastic scattering, and radiative capture is also important for neutrino detection. We have lots of techniques. I am going to zoom into a few of them starting in the next couple of lectures. I can't possibly cover all of them. You'll probably see others in some of the other lectures. But in practice, one of the really big things is not even so much the signal, but about the background and distinguishing the signal from background. And we'll talk more about that for some examples in the next couple of lectures. So next couple of lectures, I think I might have 1 or 2 more slides here. Yeah, so this is just saying what I'm going to zoom in on tomorrow. And we'll use some of this knowledge from this lecture in the discussion tomorrow. Okay, so I see a question. Are muons still the most important background at super K? That depends on the particular analysis. So they are actually, because of the structure of super K, it's actually very good capability to reduce that background. So super K has a inner detector and then an outer detector. And so cosmic rays that come in from outside will make a signal in the outer detector and the inner detector, whereas neutrinos only make a signal in the inner detector. And it's actually very efficient. We have very, very efficient techniques for removing the cosmic ray muons from the high energy neutrino background, and actually from the low energy neutrinos too. And so muons are not, actually for most analyses, are not the most important background. For some, and actually for solar neutrinos, it's radiologicals are the most important background. It's actually radon in the water and other actually cosmogenic radiation, so spallation products. So those are the biggest backgrounds at low energy. At high energy, there are, I think, actually probably cosmic rays probably are still the biggest background, but they're still a very small background. That signal is very clean, actually very low background in general for the GeV scale and beam neutrinos. It's a very clean signal. We do have some background from flashers, phototubes that are emitting light, but so muons are, it may be strictly the most important background, but it's still a very small background for high energy. And for, very specific analyses, they may still be backgrounds, like for supernova relic neutrinos. In fact, muons, cosmic ray muons are the biggest background right now. Okay, yeah, so more other questions or anything? I guess it's the end of the day, so it's a... Oh, so if you like the polls, I will come up with more of them for tomorrow. So I think it's kind of good for getting people, making sure you're awake, making me awake too.
Yeah, I think it's a great way to have some feedback. Yeah, and tomorrow it should work better. Now that I know how to properly make this happen.
Yeah, I think we're working at the end.
Okay, well, Kate, thank you so much for this talk. It was really wonderful. And yeah, we will continue with your lectures tomorrow, again at the same time slot. And we will see all the other students in the morning for Ronnie's talk. Okay, well, thank you again. That was really beautiful. Thank you.
Thank you. All right, look forward to seeing you tomorrow. Bye.
Bye-bye.